Welcome! In this session, we'll explore the problem minimum flips to make A or B equal to C. Together, we'll dive into the logic of determining how many bit flips are needed to satisfy the given condition, A or B equals C. Let's get started. In this problem, we are given three integers A, B, and C, and these integers are represented in binary form. The objective is to determine the minimum number of bit flips required so that the result of A or B matches C at every bit position. A bit flip simply means changing A0 to A1 or A1 to A0. The input consists of three integers A, B, and C, all of which are guaranteed to be between 0 and 10⁻⁹. The output is a single integer that represents the minimum number of bit flips needed to achieve the desired condition. This problem requires us to carefully analyze the binary representations of these numbers to compute the solution efficiently within the given constraints. For example, consider the input values A equals 2, B equals 6, and C equals 5. In binary, these numbers are represented as A equals 000, 0010, B equals 000, 0110, and C equals 000, 0101. When we compute the result of A or B, we get 000, 0110. Our goal is to modify the bits of A or B such that this result becomes exactly equal to C. To do this, we analyze each bit position. Starting with position 0, the result of A or B is 0, but C has A1, so we need to flip A0 to A1, which counts as one flip. Next, at position 2, the result of A or B is 1, but C has A0, so we need to flip the 1 to A0, which counts as another flip. Now, at position 1, the result of A or B is 1, but C has A0, so we flip the 1 to A0. This makes a total of 3 flips required to make A or B equal to C. Moving on to another example, consider the input values A equals 4, B equals 2, and C equals 7. In binary, these numbers are represented as A equals 000, 0100, B equals 000, 0010, and C equals 000, 0111. The result of A or B in this case is 000, 0110. Analyzing bit positions for this example, at position 0, the result of A or B is 0, but C has A1, so we flip A0 to A1, which counts as one flip. At position 1, the result of A or B is 1, and this matches C, so no flip is needed. Similarly, at position 2, the result of A or B is 1, and C also has A1, so no flip is needed here either. In total, only one flip is required to make A or B equal to C. Finally, let's examine one more example to further clarify the process. Take the values A equals 8, B equals 3, and C equals 10. In binary, these numbers are represented as A equals 000, 1000, B equals 000, 0011, and C equals 000, 1010. The result of A or B is 000, 1011. Looking at the bit positions, at position 0, the result of A or B is 1, but C has A0, so we flip the 1 to A0, which counts as one flip. At position 1, the result of A or B is 1, and this matches C, so no flip is needed. At position 3, the result of A or B is 1, but C has A0, so we flip the 1 to A0, which counts as another flip. Lastly, at position 4, the result of A or B is 0, but C has A1, so we flip A0 to A1. This makes a total of 3 flips required to make A or B equal to C. It's also important to consider edge cases in this problem. For instance, if A equals 0, B equals 0, and C equals 0, no flips are needed because A or B already equals C. If A equals 0, B equals 0, and C equals 1, only one flip is required to change A0 to A1. Another interesting case is when A equals 10⁻⁹, B equals 10⁻⁹, and C equals 0. Here, all 1 bits in the result of A or B must be flipped to 0. Finally, if A equals 0, B equals 0, and C equals 10⁻⁹, we would need to flip all 0 bits in A and B to match the 1 bits in C. These examples highlight the need to carefully analyze the binary representations to handle all possible scenarios efficiently. To solve the problem minimum flips to make A or B equal to C, the goal is to determine how many bit flips are needed to ensure that the result of A or B matches C for all bit positions. The brute force approach starts by iterating through each bit of the integers A, B, and C. For every bit position, we calculate the result of A underscore I or B underscore I by isolating the ith bit of A and B. Then, we compare this result to the ith bit of C, which tells us if a flip is necessary. For example, if A underscore I or B underscore I does not equal C underscore I, we count a flip. A key observation here is that each bit can be treated independently of others, meaning we can process one bit at a time using bitwise operations like AND, OR, and SHIFT to extract and modify individual bits. While this approach is already optimal in terms of time complexity, 32, since integers are represented as 32-bit numbers, there's room to simplify the logic further with cleaner bitwise expressions. This approach requires no additional space, making its space complexity 1. However, it involves slightly more explicit computations than necessary, which we can refine further. Now, let's look at a more optimized approach that focuses on direct bitwise manipulation. For each bit position, we extract the ith bits of A, B, and C using the expressions AI and 1, BI and 1, and CI and 1. Once we isolate the bits, we use the truth table for A underscore I or B underscore I to determine how many flips are needed. If C underscore I is 1, at least one of A underscore I or B underscore I must be 1. If both are 0, a single flip is required. On the other hand, if C underscore I is 0, both A underscore I and B underscore I must be 0, so for every one in A underscore I or B underscore I, we count a flip. By combining these cases and directly referencing the truth table, we avoid unnecessary computations and focus only on mismatches between A or B and C. This approach is also 32 in time complexity and 1 in space complexity, but it's more efficient because it eliminates redundant checks and leverages the clarity of bitwise operators, making the logic easier to follow. Both approaches process each bit independently and require 32 operations for 32-bit integers, but they differ in their execution. The brute force method, while effective, involves more explicit comparisons and slightly less concise reasoning. In contrast, the optimized approach simplifies the process by directly using the truth table for A or B and deriving the flips needed in a streamlined manner. This reduces the number of conditional checks and improves clarity. The optimized approach stands out as the chosen strategy because it minimizes redundant computations, is straightforward to implement, and requires no additional space. Furthermore, its independence of bit positions ensures scalability to larger integer sizes, like 64 bits, without additional complexity. By focusing on direct bitwise manipulation, this method provides both efficiency and simplicity, making it the ideal solution for this problem. To solve this problem, we need to determine the minimum number of bit flips required to ensure that the condition, or B equals C, holds true for all bit positions in the binary representation of the given integers A, B, and C. A bit flip means toggling a bit from 0 to 1 or from 1 to 0. First, we process the input by taking the integers A, B, and C. Then, we evaluate their binary representations bit by bit. This is done by iterating through each bit position, which involves right-shifting the integers repeatedly to isolate the least significant bit, or LSB, at each step. The LSB of any number can be extracted using the bitwise AND operation with 1, written as x and 1. Once we isolate the bits from A, B, and C, we analyze their values to determine if a flip is needed to satisfy the condition, or B equals C, at that bit position. At each bit position, we compute the result of A underscore I or B underscore I, using the isolated bits A underscore I and B underscore I from A and B. This result is then compared to the corresponding bit in C, denoted as C underscore I. If the condition A underscore I or B underscore I equals C underscore I is already satisfied, no flips are needed for that bit. However, if the condition is not satisfied, we analyze the situation further. If C underscore I is 1, at least one of the bits A underscore I or B underscore I must be flipped to 1. If one of these bits is already 1, no additional flips are necessary. On the other hand, if C underscore I is 0, both A underscore I and B underscore I must be flipped to 0, but only if they are currently 1. To keep track of the number of flips required, we use a counter variable called flips, which we increment based on these conditions. Once all bit positions are processed, the final value of flips represents the total number of flips needed. This approach ensures that we evaluate every bit efficiently and systematically. The key insight here is to minimize flips by leveraging the conditions for each bit. When C_i is 0, both A_i and B_i must be 0, ensuring the condition is met with minimal changes. Conversely, when C_i is 1, at least one of the two bits must be 1, which can often be achieved with just one flip if necessary. This ensures an optimal number of flips for each bit position. In terms of efficiency, the algorithm operates in O(n) time, where n is the number of bits in the binary representation of the largest input number among A, B, and C. Since integers are typically represented in 32 or 64 bits, this is effectively constant time for most practical applications. To implement the solution, we use a few key variables, including flips to track the number of flips, and the integers A, B, and C for processing. We rely on bitwise operators like n to extract the least significant bit and to shift the bits right, allowing us to traverse through all bit positions efficiently. The pseudocode illustrates these steps clearly. The pseudocode for the algorithm continues by handling the conditions for the flips. If A_i or B_i equals C_i and C_i equals 1, we increment the flips counter by 1 since at least one of A_i or B_i must be flipped to 1. If C_i equals 0, then both A_i and B_i need to be flipped to 0, and we increment the counter by the sum of A_i and B_i because each one must be flipped individually. After evaluating the current bit position, the algorithm right shifts A, B, and C by one bit to move to the next position. This process continues until all significant bit positions have been processed, which is determined by checking whether any of the three numbers still have non-zero bits. Once the loop exits, the flips counter holds the total number of flips required, which is then returned as the result. This systematic approach ensures that all scenarios are handled correctly, including cases where no flips are needed, as well as those requiring multiple flips at individual bit positions. The algorithm also effectively handles various edge cases. For example, when all inputs are 0, such as A equals B equals C equals 0, the loop terminates immediately without incrementing the flips counter, as no flips are required. If the condition, A or B equals C, is already satisfied for all bits, the algorithm also avoids unnecessary computations and returns 0 directly. Another edge case involves inputs of unequal lengths, where the binary representations of A, B, and C differ in the number of bits. The loop ensures that all relevant bit positions are processed by continuing until all three numbers are fully shifted to 0. For very large numbers, the algorithm remains efficient, as it only processes significant bit positions. In terms of complexity, the time complexity is O(n), where n is the number of bits in the largest input number. The space complexity is O(1), since no additional data structures are used, and the algorithm relies solely on a few variables. This makes the solution both time-efficient and space-efficient for practical scenarios. This Python implementation solves LeetCode problem number 1318, minimum flips to make A or B equal to C. The goal is to determine the minimum number of bit flips required to make A or B equals C, true for all bit positions of the integers A, B, and C. The function minFlips begins by initializing a counter flips to 0, which will track the number of bit flips needed. The algorithm processes the binary representations of A, B, and C bit by bit, starting with the least significant bit, rightmost bit. Inside the main loop, the least significant bits of A, B, and C are retrieved using the bitwise AND operation with 1. This isolates the rightmost bit of each number. Based on the value of the current bit in C, bit_C, the algorithm decides whether flips are needed. If bit_C is 0, both bit_A and bit_B must also be 0 to satisfy the condition, A or B equals C. In this case, the algorithm increments flips by the sum of bit_A and bit_B, since these bits must be flipped to 0 if they are currently 1. If bit_C is 1, at least one of bit_A or bit_B must be 1. If both are 0, one flip is required to make one of them 1. After processing the current bit, all numbers are right-shifted by one position, using the equals operator, to move to the next bit. This continues until all bits in A, B, and C have been processed, i.e., all three numbers become 0. Finally, the function returns flips, which contains the total number of bit flips required. This approach is efficient, as it processes each bit of the three numbers once. The time complexity is O, max, number of bits in A, B, C, and the space complexity is O, 1, since no additional data structures are used. Here, we start with the definition of a Java class named solution, which includes the method minflips. This method takes three integers, A, B, and C, as input and calculates the minimum number of bit flips required to make the bitwiser of A and B equal to C. We initialize a variable flips to 0, which will keep track of the total flips needed. The while loop ensures that we process all the bits of A, B, and C until all of them become 0. Inside the loop, we extract the least significant bits of A, B, and C using the bitwise in operation with 1. These least significant bits are stored in bit A, bit B, and bit C, respectively. Next, we check the value of bit C. If bit C is 0, both bit A and bit B must also be 0 to satisfy the condition, so we add their sum to flips. On the other hand, if bit C is 1, at least one of bit A or bit B must be 1. In this case, if both bit A and bit B are 0, we increment flips by 1. Finally, we right shifted B and C by 1 bit to process the next least significant bit in the next iteration of the loop. After the while loop completes, we return the total number of flips stored in the flips variable. This value represents the minimum number of bit flips required to make the bitwiser of A and B equal to C. This approach ensures that we examine each bit of A, B, and C in a systematic manner, processing one bit at a time, and making the necessary adjustments with minimal computational overhead. The algorithm is efficient and operates in O, n, time complexity, where n is the number of bits and the largest of the three numbers. By the end of this method, we have a clear and optimized solution to the problem. Here, we start with the first example where A is 2, B is 6, and C is 5. In binary, these values are represented as 0, 10, 110, and 101, respectively. Initially, we set the flips counter to 0. Now, let's process the least significant bits of A, B, and C. We see that bit underscore C is 1, which means at least one of bit underscore A or bit underscore B must also be 1. However, both bit underscore A and bit underscore B are 0, so we increment the flips counter by 1. After this step, flips becomes 1. Next, we right shift all the numbers, which gives us A as 1, binary 001, B is 3, binary 011, and C is 2, binary 010. Moving on to the next set of bits, bit underscore A and bit underscore B are both 1, while bit underscore C is 0. Since bit underscore C is 0, we need both bit underscore A and bit underscore B to be 0, which means we increment flips by 2 1 for each bit. This brings flips to 3. After another right shift, the values become A as 0, B as 1, and C as 1. Now we process the most significant bits. Bit underscore A is 0, bit underscore B is 1, and bit underscore C is 1. Since bit underscore C is 1, at least one of bit underscore A or bit underscore B must also be 1. This condition is already satisfied, so no flips are needed, and the flips counter remains at 3. After a final right shift, all the values A, B, and C become 0, signaling the end of processing for this example. The final output for flips is 3. Moving to the next example, we have A as 0, B as 0, and C as 7, which in binary are represented as 000, 000, and 111, respectively. Again, we initialize the flips counter to 0. Starting with the least significant bit of this example, bit underscore A and bit underscore B are both 0, while bit underscore C is 1. Since bit underscore C is 1, at least one of bit underscore A or bit underscore B must also be 1. Both are currently 0, so we increment the flips counter by 1, making flips equal to 1. After a right shift, the values become A as 0, B as 0, and C as 3. Next, we process the second bit. Again, bit underscore A and bit underscore B are both 0, and bit underscore C is 1. As before, we need at least one of bit underscore A or bit underscore B to be 1, so we increment flips by 1 again, bringing the total flips to 2. After another right shift, we have A as 0, B as 0, and C as 1. Finally, we process the most significant bit. Just like before, bit underscore A and bit underscore B are both 0, while bit underscore C is 1. This means we increment flips by 1 once again, resulting in flips equaling 3. After a final right shift, all values are 0, and the processing ends. The final output for this example is flips equals 3. Now let's analyze the third example, where A is 8, B is 3, and C is 10. In binary, these values are represented as 1000, 0011, and 1010, respectively. We start by initializing the flips counter to 0. Processing the least significant bit, we find bit underscore A is 0, bit underscore B is 1, and bit underscore C is 0. Since bit underscore C is 0, both bit underscore A and bit underscore B must also be 0. Here, bit underscore B is 1, so we increment flips by 1, making flips equal to 1. After a right shift, the values become 1 as 4, binary 0100, B is 1, binary 0001, and C is 5, binary 0101. Next, we examine the second bit. Bit underscore A is 0, bit underscore B is 1, and bit underscore C is 1. Since bit underscore C is 1, at least one of bit underscore A or bit underscore B must also be 1. This condition is already satisfied, so no flips are necessary, and the flips counter remains at 1. After another right shift, the values become 1 as 2, B is 0, and C is 2. Continuing with the next bit, bit underscore A is 0, bit underscore B is 0, and bit underscore C is 1. Since bit underscore C is 1, at least one of bit underscore A or bit underscore B must be 1. Here, both are 0, so we increment flips by 1, making flips equal to 2. After a right shift, the values are updated to A is 1, B is 0, and C is 1. Finally, we process the most significant bit. Bit underscore A is 1, bit underscore B is 0, and bit underscore C is 1. Since bit underscore C is 1, at least one of bit underscore A or bit underscore B must also be 1. This condition is satisfied, so no flips are needed, and the flips counter remains at 2. After a final right shift, all values become 0, completing the processing. The final output for this example is flips equals 2. To analyze the time complexity of this solution, we start by examining the operations performed in the loop. Each iteration processes the least significant bit of the integers A, B, and C using bitwise operations such as AND to extract individual bits. These bitwise operations, including extracting a bit or performing a right shift, are constant time operations, or O1. The loop itself continues running as long as at least one of the integers A, B, or C is not 0. The number of iterations depends on the number of bits in the largest of these three integers. Specifically, if the largest integer requires n bits in its binary representation, the loop will execute O log n iterations, where n is the maximum value among A, B, and C. Combining the constant time operations within each iteration and the logarithmic number of iterations, the overall time complexity of the solution is O log max A, B, C. Now, turning to the space complexity, the solution's memory usage is independent of the size of the input. The algorithm maintains a fixed set of variables such as flips to count the changes, and bit underscore A, bit underscore B, and bit underscore C to store the current bits being processed. These variables require constant space, or O1. Additionally, the input integers A, B, and C do not introduce extra space overhead because their memory usage is inherent to the input itself. Importantly, this algorithm does not rely on any additional data structures, arrays, or recursion stacks, which means there is no extra memory allocation beyond the constants mentioned. As a result, the overall space complexity is O1. By comparison, a brute force approach involving the generation of all possible bit combinations would not only be computationally expensive but also memory intensive, with a potential exponential time complexity of O2 to the power of n. The current solution avoids such inefficiency and achieves logarithmic time complexity with constant space usage. Looking at the best, average, and worst-case scenarios, we observe how the algorithm adapts to different input sizes. In the best case, all three integers A, B, and C are already 0. Since the loop condition is not met, the algorithm terminates immediately, resulting in O1 time. On average, the number of iterations corresponds to O log max A, B, C, because the loop processes each bit of the largest integer. Each iteration performs constant time operations, maintaining the overall time complexity of O log n. The worst case occurs when the integers are at their maximum size, such as a 32-bit or 64-bit integer limit, causing the loop to iterate through all bits of the largest number. Even in this scenario, the time complexity remains O log n. To justify this mathematically, note that the number of bits required to represent an integer is proportional to the logarithm of the integer's value. Since the algorithm processes each bit exactly once with constant time operations, the total time complexity scales with the number of bits, i.e., O log max a b c. The space complexity remains O1, as no additional memory is allocated beyond the fixed set of variables used in the algorithm. When tackling this problem, there are several common mistakes to watch out for. First, ignoring leading zeros in binary representation can lead to errors. This happens when you assume that A, B, and C always have the same number of bits, which is not true unless you explicitly pad their binary representations to the same length. Tools like Python's fill or bit masking can help ensure uniformity. Another issue is not handling edge cases, such as when C is all zeros or all ones. For example, if C is 0, every bit of A and B must also be 0, requiring flips wherever they are not. Testing these extreme cases, like C equals 0 or C equals 2 to the power of n1 for n-bit numbers, is critical. Finally, many misunderstand the OR logic itself. Remember, 0 or 1 results in 1, as does 1 or 1, but flipping the wrong bit can lead to unnecessary operations. Always go back to the OR truth table and verify your calculations at the bit level. Another frequent pitfall is writing inefficient implementations. For instance, using nested loops or performing string manipulations on binary representations can significantly degrade performance, especially for large inputs. Instead, leverage direct bitwise operations like AND and caret to process each bit in O(n) time. Additionally, some overcomplicate the problem by focusing on all possible combinations of A and B, which is unnecessary. The key is to recognize that each bit position is independent of the others. By solving for each bit position separately, you can simplify the logic and avoid redundant calculations. This problem is a classic example of bit manipulation, which is a favorite topic in technical interviews. Interviewers often want to see how well you can handle individual bits efficiently. One key optimization here is to realize the independence of each bit. For instance, if a bit in C is 0, you must ensure that the corresponding bits in both A and B are 0. On the other hand, if the bit in C is 1, you need at least one of A or B to have a 1 in that position. Additionally, interviewers might explore variations, such as minimizing flips for A and B equals C or extending the problem to more variables, like A or B or D equals C. Be prepared to handle scenarios with larger integers, such as 64-bit numbers, and think about how your approach might scale. This problem is closely related to several others that focus on bit manipulation. For example, problem 136, single number, uses XOR operations to identify a unique number in an array. Problem 338, counting bits, challenges you to count the number of set bits efficiently. In problem 190, reverse bits, you'll manipulate the bit order within a number. Finally, problem 201, bitwise and of numbers range, involves using bitwise operators to solve range-based issues. Exploring these problems can deepen your understanding of bitwise techniques and help you recognize patterns across different challenges. There are multiple approaches to solving this problem, each with its own trade-offs. A brute force approach involves iterating over each bit of A, B, and C, flipping as necessary. While this method is straightforward, it can become inefficient for large numbers. A more optimal approach leverages bitwise operations like AND to directly calculate the required flips for each bit, achieving linear runtime. For even greater efficiency in repeated queries, you can use pre-computed masks for common cases, like all ones or all zeros, and apply them as needed. However, this method increases memory usage, so it's important to weigh the trade-offs based on the context of the problem. Thank you for joining. Today, we learned how to solve the problem minimum flips to make A or B equal to C with a clear and efficient approach. By analyzing each bit, we developed a simple and effective solution. Remember, mastering bitwise operations is crucial for tackling a wide range of problems. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!